Yes, in the above discussion, you have seen that in traveling from point X to point Y, point X to point Y, electric potential increased. Point X to point Y, you traveled against the electric field, electric potential increased. So, in general, we can write a relation like this, VA minus VB. This relation is very important in problem calculations concerned with electric potential. VA minus VB equal to minus of integration from B to A. Minus of integration from B to A E bar dot DL bar. That is, if at all you travel from B to A, if you travel from B to A in the direction of electric intensity as the reference, electric potential decreases. So, VA minus VB can be written as what? VA minus VB minus integral of B to A E bar dot DL bar. Able to follow? So, this we can apply in many problems based on this integration, a very important relation to find the potential difference between 2 points when electric field vector is given. In this topic, electrostatic potential and capacitance, today let us discuss about these topics: potential energy of system of charges, potential energy in an external electric field, and electrostatics of conductors. Right. Now, let us discuss regarding the potential energy of system of charges. For that, let us say a point charge Q1 is already available here. A point Q1 is already available. There is a point here whose distance is smaller from this. Now, let us go to infinity and catch hold of another point charge Q2. Let us catch hold of another point charge Q2 from infinity and bring it and put over here. Then that is the meaning of grouping of 2 point charges here, Q1 and Q2, with the separation of distance R between them. Before that one, because of this charge Q1, what is the potential here? V1. So, because of this charge plus Q1, potential here is V1, that can be expressed as V1 equal to 1 by 4 pi epsilon naught Q1 by R. So, what is this value? It is a potential at this particular point because of this plus Q1 charge. Then here potential because of this one is over here. Now, let us go to infinity and catch hold of another point charge Q2 and bring it over here. And what is the meaning of this potential? Work required to move a unit positive charge from infinity to a point. That means from infinity to bring a unit positive charge and put it over here, this is the amount of work done. But now we are carrying a charge plus Q2 from infinity, plus Q2 from infinity, and we are bringing it from here to here. On a unit positive charge, if the work done is V1 to bring a point charge Q2, from infinity to this point, the amount of work done will be Q2V. Able to follow? So, potential because of this one here, because of this, potential here is this, and to bring another point charge Q2 from infinity to this point, the amount of work to be done is what? W equal to Q2V. Now, simply Q2V1, potential at this point is V1. Now, put the value of this V1 over here, you can see that the work done is 1 by 4 pi epsilon naught, right, Q2 Q1 by R. So, this is the work done against, it is the work done against electrostatic conservative forces to arrange these two charges together. That means to bring that Q2 from there and put it over here, that becomes an arrangement of 2 point charges Q1 and Q2 with the distance of r between them. The amount of work done is this. Now, this amount of work done only will appear as potential energy in that system of charges. So, in the system of 2 point charges Q1 and Q2 separated by distance of r between them, the amount of potential energy stored will be this one. This is only the potential energy, because potential energy within the system of 2 point charges, that is potential energy of system of charges. And one more way we can understand is, if many charges are grouped together, if many point charges are grouped together, between each pair of point charges, this much amount of potential energy will be there. Therefore, if a number of point charges are combinedly given there as an arrangement, you have to calculate first, you have to find how many pairs are existing. Between each pair, this amount of potential energy will be there. Let us see now how to calculate that. Okay, now, and if at all here this kind of system of point charges are given, there are 4 charges here formed into a single system. We should find how many pairs are existing. Between each pair there will be electrostatic potential energy. So, Q1, Q2 is a pair, Q2, Q3 is a pair here, Q3, Q4 is a pair, and Q4, Q1 is a pair here. Now, Q1, Q2 will exist, right? Q2, Q3, Q3, Q4, Q4, there is this. Then, next, this Q3, Q1 will exist. Okay, each combination, let us see here how many pairs they will be existing. Total potential energy of the system, let us see with first pairing here. That is how many pairs this will form with the other charges. Therefore, total potential energy equal to here 1 by 4 pi epsilon naught. Let us take it as common. Now, pairs with Q1 is Q1, Q2 by R1 plus Q1, Q3. This pairing is over, right? Next, this pairing, let us call it as what here, R5 distance. Therefore, next potential energy is Q1, Q3 by R5. So, there is no importance of these numbers here, only to represent what different distances. Next, one more pair, what this Q1 form is Q1, Q4 by R4 plus Q1, Q4 by R4. So, here what we calculated, potential energy in this pair, potential energy in this pair, potential energy in this pair, right. Next, let us go to 3 pairs are over here. Next, let us take pairing of this one now. This pairing is over. How many pairs Q2 will form with the other charges? Q2, Q1 is already discussed here. Q2, Q1 pair is already over. Now, Q2, Q3 with the distance of R2. Therefore, Q2, Q3 distance R2. This and this pair. Next, this and this pair. So, let us call only for convenience purpose this distance as R6. Now, Q2, Q4 by R6. So, now what happened here now? Initially, pairs formed by Q1 is taken, 3 pairs it formed, Q2 formed now 2 pairs here, 1 pair is this, other pair is this one, right. And Q2, Q1 pair already discussed. Now, pairing of this is over, pairing of this is over. Next, pairing of this one. Let us go to now, these 2 are over now. Next, this. Do systematically. Now, Q3, Q2 pair already considered. Q3, Q1 is already considered. Only this pairing is left over now. Plus, so one more pairing, potential energy. Q3, Q4 by R3. Q3, Q4 by R3. And that is what this pairing with this is already over, with this already over, only with this the pairing is left over. The pairing potential energy between Q3 and Q4 is what? R3 here, and Q4 pairing with this is over, with this is over, with this is over. There is no other pairs formed here. This is the total potential energy of the system, 1 by 4 pi epsilon naught, 3 pairs for this plus 2 pairs for this one plus 1 pair for this particular one. So, this is the when a system of point charges are given, how many pairs they are getting formed. Between each pair there will be electrostatic potential energy, there will be electrostatic potential energy, and sum of this all the potential energies is nothing but this value here. It is a method of calculation. If many point charges are given at the corners of a equilateral triangle or at the corners of a square, etc., simply find how many pairs are available. Between each pair this amount of potential energy will be like this. Yes, now let us go to the next point of discussion, potential energy in an external electric field. Now, suppose there is an external electric field. In this one, there is a stake what a case of there is an external electric field, and because of external electric field, right, there is a point here with potential V. Because of external electric field, because of already existing electric field, because of some other agent charges, there is electric field already present there, and in that already present electric field there is a point of electric potential V. Now, if there is a charge Q present here, that is, in the external electric field of electric potential V, a charge Q is present here. So, what is the potential energy of this particular charge? So, from the concept of starting electrostatic potential only, if V is the potential here, what is the meaning of it? Work to move a unit positive charge from infinity to this point is this, but charge Q is available here. Charge Q available means what? A charge itself will not be available in the electric field. Some external agent has to bring it. Therefore, if V is the electric potential means to bring a unit positive charge from infinity to this point is V, and charge Q is available. Charge Q is available means somebody brought it. So, what work that other agent has done to bring this charge Q from infinity and place here, that is nothing but potential energy U equal to QV. Therefore, what is the situation? This is the situation of if there is a point of electric potential V, where electric potential V is because of an external electric field. At that point, a point charge small q is already available, means somebody brought it and put over there. Whichever the work done by that external agent, that will appear as what? Electrostatic potential energy over there. Therefore, U equal to QV in the external electric field. So, if a charge Q is present in the external electric field of potential V, the potential energy is this. Next, let us go to one more situation of, right, external electric field. There is external electric field, the potential is V everywhere, say. Then two charges are present here, charge Q1 is present and charge Q2 is present with a separation of R between them. There is an external electric field here. Everywhere the electric potential is what? V. Then in that electric field, two charges are present. Two charges are present means they will not be present by themselves. Some external agent only brought them. So, some agent brought Q1 and put over here. Some agent brought Q2 and put over here, and a distance of small r is maintained over here. Right. So, in this context, total potential energy let us calculate. Right. So, this Q1 is available at the point of potential V here. So, because of Q1 availability due to this potential, potential energy is Q1V plus Q2 is available at the point of potential V. Therefore, potential energy due to availability of Q2 at the point of potential V is nothing but Q2V Then Q1 and Q2 got arranged here. Q1 and Q2 got arranged here, right, against their electrostatic force of repulsion. So in that case, the potential energy between this pair of charges is 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught Q1 Q2 by R. So total potential energy of this system of two charges with separation of R between them in the external electric field, and everywhere the potential is V, total potential energy is this. So like this we can calculate what? Potential energy of system of charges when there is no other electric field is present, and potential energy of the system of charges when external electric field is present, and because of external electric field the potential is nothing but V over here. This is the calculation of total electrostatic potential energy. Yes, dear students, now let us discuss about electrostatics of metallic conductors. A metallic conductors will have free electron cloud, so that electrons can move everywhere, right, freely from one point to the other point. And if at all a metallic conductor is charged, up, even if charge is given interior also, if metallic conductor is charged up, that entire charge will appear on the outer surface only. That is, on any metallic conductor system, if at all the metallic conductor is charged under static conditions, we are discussing here no electric current, all those things over here, static condition, charges are at rest. Under static conditions, whichever the electric charge that is given to the conductor, it will reside on the outer surface only. A point can come here, why sir, why the charge should appear on the outer surface only? That is to have least potential energy for the charge distribution. In the nature, every system will try to attain minimum potential energy. For example, between the pair of charges, the potential energy is 1 by 4 pi epsilon naught Q1 Q2 by R. For potential energy to be least, small r should be what? Very, large over there. That means, if at all two free charges are given, no other boundaries are present, no other restrictions are present, those two charges will try to go to infinity. With separation, with full repulsion, the charges will try to appear to go at infinity to have what? Large separation as possible, so that potential energy of the system becomes zero when R becomes infinity. So, for any metallic charged conductor, whichever the entire charge that is given, that entire charge appears on the outer surface only to have minimum potential energy for the charge distribution. For that reason, one point we can tell here is entire charge is on the outer surface only, right? No electric charge, no electric lines of force inside. So E equal to 0 at every point inside. So inside an metallic charged conductor, electric intensity equal to 0. Right? If electric intensity is not 0, you remember, if electric intensity is not 0, then there can exist potential difference also. Because of potential difference, it is a pure conductor over here. If at all there is a potential difference across a pure conductor, electric current can exist and lot of heat generation by itself, all those things will take place, but those things are not possible. Therefore, E equal to 0 at every point inside a conductor. If E equal to 0, right, what you can expect is what? Everywhere potential will be the same thing. E equal to 0. One more point we discuss why the potential is same at every point here. So first of all, entire charge distribution on the outside only, E equal to 0 at every point inside the conductor. Now second feature what you can do is, what we can expect here in case of electrostatics of metallic conductors. Right? First point is E equal to 0, entire charge on the outer surface. Second one, can you expect any net charge somewhere over here, right? Some Q charge somewhere over here. If there is Q charge somewhere over here, by applying Gauss law, you should get net electric flux. There will be net electric flux, but E equal to 0 at every point inside the conductor, E equal to 0. If E equal to 0 there, according to Gauss law, right, net electric flux, that is line integral of E bar dot ds bar should be Q in by epsilon naught, that should be equal to 0. And here E inside is 0, right? There is no electric intensity inside. So that automatically implies that at any point inside a conductor, there will be no net amount of electric charge. And if at all there is a net amount of electric charge, right, then this line integral will not become 0. When line integral will not become 0, E will not become 0, but E should be 0. So for that reason, at any point inside any charged conductor, there will be no net amount of electric charge. First one and second points regarding it. I think things are clear. E equal to 0, entire charge is in the outer surface. Second one, there is no net amount of charge at any point inside. Now, the surface of any charged conductor, third point you can note down. The surface of any charged conductor should be an equipotential surface under static conditions. That means electric potential at any point on the surface. For example, potential at this point is V. Then what I mean to say is potential at this point also V only. Here also potential V, here also potential V. It should be. Surface of any charged conductor should be an equipotential surface. Otherwise, if you say that here and here potentials are not same, that means there will exist a potential difference across the points of a conductor. That is, here and here there is a potential difference. Say here high potential here, there is a low potential here. Automatically currents will set up. Across the surface of the conductor, and conductor very low value of resistance because of no potential difference existing here, very high currents will exist, and high amount of heat energy will be developed by itself. So that type of things are not there. That is, currents will not exist on only charged conductor. There should not be any interior current flow. Therefore, this point and this point should be having same potential. Similarly, if this is a potential V, potential here, everywhere potential must be same thing. That means surface of any charged conductor is an equipotential surface. If the potential here is V, potential here also must be equal to V, right? Everywhere the potential must be V. Then what about any interior point? For example, there is a point X inside. That is, on the surface of the charged conductor, everywhere potential is V. There is a point X inside the conductor, and we have to say that, we will say that at this point also potential should be V. Why potential should be V there? If at all potential is not V there, here potential is V. Suppose high potential here than this one, right? If at all high potential when compared to this one, potential difference from here to here, currents will automatically flow. Automatically flow from high potential to low potential within that only charged conductor, and that is again is the right principles of energy. Heat energy will be automatically developed by itself, currents will flow by itself. So what we mean to say here is, surface of any charged conductor is an equipotential surface, and potential must be same everywhere at every point on the surface. That same potential must be at every point, even inside the conductor also. Therefore here at this point we should note that this entire thing is nothing but equipotential surface. Everywhere also same potential must be there. V in equal to Vs equal to constant. Able to follow? Surface of of any charged conductor, everything should be an equipotential surface, same potential everywhere inside and equal to that on the surface. Next, from the concept of equipotential surfaces, one point we understood very clearly that electric intensity will be always perpendicular to the equipotential surface. Therefore, E equal to 0 everywhere inside, that is okay. But what about electric intensity at every point outside? Now, this is an equipotential surface. It is an equipotential surface. At every point, electric potential, electric intensity must be normal to that surface. Electric intensity must be normal to the surface at every point. So, outside or at any point on the surface of the conductor, electric intensity must be normal to the surface, because surface of the conductor is an equipotential surface. Therefore, that E bar can be expressed as, and in the previous chapter you found the derivation, electric intensity because of a charged conductor, and that E bar vector can be written as E bar equal to sigma by epsilon naught n cap. Electric intensity at every point on the surface of a charged conductor, sigma by epsilon naught n cap, where sigma is the surface charge density. Surface charge density, n cap is a unit vector. N cap is a unit vector normal to the surface and outward from the surface. That is, n cap direction is like this. This is n cap direction. Unit vector normal to the surface. Unit vector normal to the surface, and it is outward normal. Outward normal to the surface. This is unit vector. Therefore, at any point on the surface of the conductor, electric intensity, and two more points you learn now. What is that? E equal to 0 everywhere, surface must be equipotential. Therefore, electric intensity must be normal to the surface of the conductor at any point in the field.